Same idea now for chromium. So that's our table, there's chromium. So we'll go 1s2, 2s2, 2p6, which is already given us. So now we're at neon. Now we'll come down here to the 3s's, go 3s2, leap over here to the 3p, go 3p6. Down here for the 4s, 4s2, and then into the 3d, 1, 2, 3, 4. So if I was an unthinking student, I would go ahead and say, right, 3s2, that's easy, 1 up, 1 down. Now we go into the 3p's, up, 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 down, down, down. Then I'll do the 4s's because those are what come next in the periodic table. So we'll go there, 1 up, 1 down. And now we'll come to the 3Ds. We've got to put 4 electrons. So up, 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 up. But then, of course, the thinking student remembers that, well, you're 1 electron short here of a half-filled D subshell. And there's extra stability from that. So what we'll do is we'll take one of those electrons in the 4s that's repelling the other one anyway, and pop it into the 3D. So thus we actually have 4s1, 3d5 at the end, and there's the arrows in there nicely. So now a nice question on relative ionization energies. State which of the following statements is true. So that's our ionization energies, and of course it increases as we go up a group, increases as we go from left to right, remembering of course that little staggered bit whereby it goes lithium up to beryllium, down to boron, up to carbon, up to nitrogen, down to oxygen, and so on. But anyway, let's see if we need to know all of that. First, ionization energy of neon and helium. Well, there we go. Neon is actually lower than helium, so therefore neon would be lower than the ionization of helium. Sodium there versus neon there. Well, we can see that not only are we going up, we're also going all the way across to get from sodium to neon. So that means that sodium will definitely be less than neon. Ionization energies increase down group 1. No, they increase as you go up group 1. So that means they decrease as you go down group 1. And then the second ionization energy of sodium less than the first ionization energy of sodium. Absolutely not. All second ionization energies are greater than the first ionization energies for every single element out there because it gets harder to remove successive electrons. Now we have a question I think I made too much of a meal of here, but anyway, so we got the log of the successive ionization energies. Well, that's just because it makes it a prettier little curve using the log instead of the actual values, but it's still the same idea. The greater the value, the greater the log. Using the electron configuration, discuss how and why the values change according to the number of electrons removed. And what we see as we go along here is we're removing more and more and more electrons. Well, the first thing is that the trend is obviously upwards, and that is because it is always harder to remove another electron, because once you've removed one electron, the nucleus is going to hold more tightly to the other ones. So removing one, then harder to remove a second one, harder to remove a third, a fourth, a fifth, and so on all the way up. So that's the general trend that we would see for any atom. But now let's think about some particular bits of this trend for magnesium. Here's our bit of the periodic table. So we start off with magnesium itself, 1s2, 2s2, 2p6, 3s2. So we'll remove the first electron, so that takes us to 1s2, 2s2, 2p6, 3s1. No big deal there, that's the energy needed. Removing the second electron, 1s2, 2s2, 2p6, 3s1 goes to 1s2, 2s2, 2p6. Again, no big deal there, although actually, of course, you might think, well, we're making a nice, pretty inert gas, noble gas electron configuration here. So it should be actually easier than you would expect to remove that electron to make such a nice, happy thing. And we would certainly discuss that if we were comparing magnesium to another element, but we're not. We're just comparing magnesium to magnesium, so all we see is that it's tougher to remove the second electron than it is the first. But then for the third one, removing the third, we see a huge big jump here. Look at that jump from removing the second to removing the third. And that's because, of course, we're taking an electron out of an inert gas, a noble gas configuration, going from 1s2 to s2 to p6 to 2p5. So it's much harder than it should be, and so that's why we see this big leap here. And remember, this is a logarithmic leap, which means the leap in actual values is much bigger. Anyway, now we see a pretty much standard little increase here. Constant increase, remembering again that to remove a fourth is always going to be tougher than the third, the fifth tougher than the fourth, and so on. So as we go through here for the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, I'm just going to click it out, show you what's happening. We're just removing an electron each time. Now, as I click it all the way down here, going up to removing the ninth one. Those of you who are really paying attention might say, okay, so I can see removing the fourth one, no big deal. Removing the fifth one, well, we're actually making a half-filled P. So therefore the fifth should be a little bit easier. And then the sixth, where we're breaking into a half-filled P, should be harder. So looking at the fifth to the sixth, you can't really see any big difference there, but that's because it's a logarithmic value. Maybe there would be where the fifth is a little bit easier than it should be and the sixth a little bit harder than it should be, but it doesn't show up when you're using logs. Same as we go down here, no big deal for the seventh or the but then we get to the eighth, we're removing a P, and so now we're down to a filled S subshell. And then, of course, for the ninth, we're breaking into a filled S subshell. So you'd expect actually, again, some little deviation for the eighth and the ninth. But you could almost imagine that that's going up a little bit. And you could certainly see that the 10th is a bit easier than it should be. But it's, again, doing logarithmic values doesn't emphasize big differences. But anyway, get down to the 10th. And when we make the 10th, we've now got another noble gas configuration. So you can see the 10th is definitively lower than it should be. If you look at this general line here, it should be a little bit higher than it is. But then, of course, you get to the 11th here, and we see another big jump because now we're breaking a noble gas configuration, and that is of massive, massive significance. So therefore, to remove the 11th one, taking it from 1s2 to 1s1 is much, much, much harder than it should be. So we see another big leap there. And then finally, the 12th one, we remove the last electron. There's nothing left. So anyway, like I say, I'm sure I made much bigger deal than I needed to be, but what you're seeing, important factors: number one, general increase upwards, because it is always harder to remove successive electrons. And then you see big jumps associated with pulling an electron out of a noble gas configuration, so removing the third electron and then removing the 11th electron. Following elements order increasing first ionization energies. So as we look at it, they're just given to us in the order that they are on the periodic table: sodium, magnesium, aluminium, silicon, and then chlorine up to the side. Generally, ionization energies increase as you go from left to right, and so we would expect this to be the order. However, magnesium and aluminium are a little bit squiffy. Magnesium, first of all, is neon 3s2. You remove an electron from that for that first ionization energy, you're breaking a filled S subshell. That is harder than it should be, so therefore the value of magnesium is higher than it should be. Going to aluminium, and it's neon 3s2 3p1. So when you remove that first electron, you're just making a filled 2s subshell. So that's easier than it should be. So magnesium higher than it should be, aluminium lower than it should be. So those values switch. So the actual order is sodium, aluminium, magnesium, silicon, chlorine. That is that same zigzag pattern we have seen several times. Using the same picture, how would we expect hydrogen to compare first of all with helium? Well, obviously, as you go across, it's getting higher, so therefore hydrogen is going to be lower than helium. And then comparing hydrogen and lithium, well, as you go up, it becomes the ionization energy increases, so therefore hydrogen is bigger, larger than lithium. For ionization energies from elements shown in the table below, state to which group the element belongs. Well, what I'm looking at here is there is a big jump as I go from the second to the third ionization energy. It's only 1320 from the third to the fourth, but it's over 3000 for the second to the third. Now that big jump occurs when you're breaking a noble gas configuration, as we've seen several times before. So what this is telling us, that our element, our mystery element, has a noble gas configuration after we've removed 2 electrons. Thus it must be in group 2, otherwise known as the alkaline earth metals. How would you expect nitrogen to compare with oxygen? We've seen this several times before, of course. Nitrogen, you've got a half-filled p subshell. So when you remove an electron, you're breaking that half-filled p subshell. That's harder than it should be. Thinking now of oxygen, starts as 1s2, 2s2, 2p4. You remove an electron, comes out that 2p4, making it 2p3. So now you've made a half-filled p subshell. That's easier than it should be. Therefore, nitrogen, while it should be less than oxygen, is actually greater than oxygen. Sodium forms only one stable ion. Insert arrows. Well, there's sodium, so we know 1s2, we already know 2s2, 2p6, 3s1. Now, we don't want the sodium atom, we want the stable ion. Well, of course, that is Na+, as all GCSE chemists know, because the sodium wants to lose an electron to become like a noble gas. So therefore, our electron configuration of interest, 1s2, 2s2, 2p6. Let's throw in those arrows, 2s, one up, one down, 2p, up, 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 down, down, down. So consider the elements labelled A through G. These are not chemical symbols. Never really see the point of this, because all you got to do is go to the periodic table and identify what they are. But let's pretend that we don't have a periodic table with us, but we can look at these electron configurations. So as we look, A, B and C, these are all in the second shell. D, E and F are all in the third shell, and G is in the fourth shell. So, which one's going to have the largest first ionization energy? Well, of course, as we go from the fourth to the third to the second shell, the ionization energy is increasing. Okay, so therefore, the one with the highest has got to be in the second shell. The reason for that is that as you go further up the periodic table, there's less shielding, there's less elements in filled shells getting between the electron and the nucleus, and the less shielded it is, the harder it is to remove the electron. But now, which of A, B and C is it going to be? Well, C is further to the right. Okay, C has got the highest nuclear charge of all of the ones A, B and C, and so therefore the nucleus is going to hold on to those second shell electrons better in C than in B, and better in B than in A. And of course, if you think about it, C is of course a noble gas, it's neon. So therefore it's going to have the highest first ionization energy. Lowest one, well, again, we'll just flip everything, reversing it, okay? As we go to the fourth shell, that's all the way down, so there's going to be much more shielding of the electron, which means it's much easier to remove the electron from something in the fourth shell than the third shell and the second shell. And of course, it's the alkali metal in the fourth shell, so therefore it's absolutely the easiest one in the fourth shell. Copper atom, well, let's just whiz through this, shall we? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9 would be the unthinking student. However, the thinking one says, well, 3d9 is really close to 3d10, and a filled d subshell is very stable, so we'll just grab one of those s electrons and pop it up into the d subshell. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3. And finally, for our electron configurations, we want cobalt. Cobalt itself, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7, right, 1, 2, 3, 4, 5, 6, 7. However, I did not want cobalt, I wanted cobalt 2+, so I have to remove 2 electrons. The unthinking student removes them from the D. The thinking student says no, they go from the highest shell, and so therefore I'll remove 2 electrons from the 4s Thus I will have 3d7 as the end of my electron configuration, because up to 3p6 is argon and is very difficult to change anything. So I lost the 4s2, leaving us with just 3d7 at the end. And that's the end of the atomic structure questions on our A-level worksheet.